All right, it is 10:30. Let's go ahead and get started. Thanks everybody for joining us today. So we are today here for Hark's Weatherization, Healthy Homes, and Climate Readiness. So appreciate you guys being here. My name is Randy Plumley. I'm the kind of the Energy Codes Program Manager for Spear, as well as for Building Performance. So if this webinar is being recorded, we will upload that to YouTube probably within 72 hours. I will have the chat feature open, so feel free to basically put anything in there if you have any questions or any technical difficulties you might be having during the presentation. I'll also have the Q&A feature open as well. You're free to use that, and we'll answer questions probably towards the end of the presentation. So we've done some recent episodes or volumes of these for Hark, I'm sorry, for the WAP program. So this one is the Healthy Homes and Climate Readiness. Some of this stuff will be from what you've seen before, but I'll put some new information in here. So who is Spear? If you're new to Spear and what we do, we are one of 6 regional energy efficiency organizations. We cover Texas and Oklahoma. We are a nonprofit. We are member-based. We have over 65 members from a wide selection of energy efficiency industries such as manufacture and others that promote and advocate for adoption of energy codes. So we're focused on outreach of education and collaboration. So that's what all I really do is do energy coach training. So thanks again for being here. So benefits of home weatherization. You guys are probably familiar with doing this on a daily basis, but just go through some real highlight uh, areas where we actually have benefits that you can tell homeowners or others in your community. First and foremost, it's reduced energy bills. That's kind of what we're out to do, but also increased comfort, enhanced indoor air quality, also reduce environmental impact, increased home value. It can help if you keep records of that and show that you've had improvements to your home. That can actually help increase home values when you go to resell it. Longer lifespan of HVAC system. It's been proven that if you fix the airflow issues or anything that's blocking airflow back to the system, it can help that thing run a little bit easier and have those fan motors last a little bit longer. You can reduce noise pollution from outside as well, decrease chances of condensation and mold growth inside the building. Also, then with that goes hand in hand with enhanced durability and reduced maintenance over time. And then lastly, of course, this comes with adding on-site generation, but there is a way that you can have a goal to get energy independence. Of course, it starts with reducing your energy consumption to begin with, so you don't have to spend so much money to have offset of on-site generation. So healthy homes and then climate readiness. So weatherization plays a critical role in enhancing climate readiness, contributing directly to a home's health and safety, which is really what all codes are about. So just looking at that, though, we have energy efficiency and climate control. So weatherization measures such as air leaks, insulating the walls, the attics, upgrading windows help improve the home's energy efficiency. This keeps indoor temperatures more stable. So you're actually conditioning the home and with heating or cooling, and you're holding that air in longer. So that helps reduce your energy consumption as well as the climate control inside. Climate readiness. So in regions where we have frequent heat waves and cold snaps, you guys may not get as many cold snaps as I do in Dallas, but you guys have a lot of other vital weather concerns as well. So weatherizing a home is better equipped and can maintain a safe indoor temperature, reducing strain on heating and cooling systems. Guys may remember Winter Storm Uri. It was kind of proven that if homes were built more to a updated code standards, that you could have sheltered in place about a day to a day and a half longer. So that's kind of what we're talking about when we say climate readiness. So indoor air quality and ventilation. So weatherization efforts often enhance ventilation systems. They prevent moisture from building up. They ensure consistent flow of what we call fresh air. In the code, it's called mechanical ventilation. We'll talk more about that later on in this webinar. So sealing leaks, reducing dust, pollen, pollutants from entering the home basically improves the overall air quality inside the home. So health implications. So poor indoor air quality can exacerbate respiratory conditions such as asthma or allergies. By maintaining a good indoor air quality, weatherization supports healthier living conditions, especially in vulnerable populations. like children or the elderly. And then the very last here, we're talking about moisture control and mold prevention. So we talked about it earlier. You seal the holes in the building and you do a better job of airflow and also bringing in mechanical ventilation. You reduce the chance of moisture buildup inside the structure. And then overall, we've got health and safety concerns that, if you've got mold growth that's leading to that, you've got serious health concern problems and damage to the home structure as well. And then, of course, resilience to climate events. We talked about that Winter Storm Uri, but you guys also are more susceptible to hurricane weather events that come on from time to time down in the further south. And of course, this can also help mitigate some of that. And then, of course, the cost savings and income security. And then, of course, heat stress prevention. In Texas, we have a lot of that, especially down south. There's a lot of heat waves that come through that are just relentless. But climates like Texas, where heat stress is a concern, weatherization, of course, as we talked about, you plug the holes and keep the conditioned air inside longer, then you can ride through that heat stress prevention a little bit easier. So I always like to go into this really talking about what we learn as I was used to be an energy professional in my previous job doing inspections for new income or new construction homes for the energy code. But basically, it comes down to building science basic, understanding that a house is a system, all parts interact together. We have common air leaks that impact comfort, durability, and energy use. So, as a weatherization crew, you're going to be looking at these point of entries or exits to try to seal these up as best that you can. So typical leakage points, attic hatches, duct registers, supply and returns, top plates, seal plates if you can reach them, vents, any kind of vents in the ceiling, recessed lighting, bath fans, kitchen exhaust pipes, dryer vent pipes, any of those that penetrate through the envelope need to be addressed. So air sealing plus better insulation is key to better performance inside the house as well as comfort of the home. So understanding that from a building science perspective gives you a better overall look of I need to connect the dots. It's not just about caulking a window, it's also plugging the holes that are on the ceiling as well as possibly taking off a light switch cover and putting gaskets behind it. It's stopping air from entering into the building or exiting the building. So with that comes hand in hand is the building's thermal envelope and building shell. As a energy inspector and or weatherization crew, you have to identify where is the conditioned and unconditioned separation points. And that's this is a simplified illustration, but you see the pink line that's there. That's identifying a starting and stopping point that separates conditioned from unconditioned. Air sealing and proper insulation needs to happen at all those areas. It really should maintain connectivity and it should never be able to have a separation point. In other words, if I was looking at this home and had a simple drawing on a piece of paper, if I put a pen on that paper and drew this pink line, I should never lift that pen off the page. It should be continuous and aligned. So the house it's made up of different areas. There's a knee wall separating attic from interior space. Could be crawl space walls. There could be floors over crawl space. We could have basements. We could have cathedral ceilings. And then, of course, we have the exterior wall, including windows and doors. So all those things need to be addressed. But all those areas make up what we call the thermal boundary, which is consisting of air barrier and insulation. So those things should be continuous and aligned at all times. So factors determining comfort, it's not in Texas especially, and in the South, even more importantly for most of the South area of the United States, it's no longer just air temperature that we're trying to get under control for comfort. Since the energy codes have made homes a lot tighter, there's a chance of possible moisture or humidity coalescing inside the building itself. So now we're not only looking at air temperature, we're also looking at relative humidity. So for both winter and summer, we've got 4 factors that we look at. Air moving in and out of the building shell, the air temperature is what you actually can feel, but then radiant temperature and relative humidity you can also feel. It's like the more humid the air is, the more it's like a warm blanket on you, and you just kind of need to mitigate that to stay comfortable. So that's what we're looking at. So back to that energy and building shell, we looked at the pink line that was drawing around the building. That was the determination of what we need for air barrier and insulation, but it also comes to an important part of where do all these heat gain and heat losses come from? And it's through that building shell, what we call the thermal boundary. But you also have different areas of how it gets through. So on this illustration, you see the sun. It's got radiant heat that hits the roof deck. That roof deck now turns into connectivity or conductivity of heat transfer. Then it re-radiates itself in the attic. It hits the insulation and makes its way into the building. We also have internal heat gains from people and from electronics and from animals. And if you've got sun coming through a window and heating up furniture or the carpet or vinyl flooring or wood flooring, those things tend to radiate heat over time. It's kind of like what we call a heat sink. It's a mass that actually is generating or it's holding heat and energy or energy and heat, and eventually it starts to re-radiate inside the building. So the total energy needed includes all these inefficiencies of equipment, plus the internal heat gains, the external heat gains, and now we need to overcome those to maintain comfort. We just saw this. This is more a close-up picture of this, but common attic air leaks. This is kind of where the weatherization crews can really get to this stuff. It's just under fluffy insulation. You remove some of that, you can now fix and plug all of these holes. We talked about top plates and seal plates at the bottom. Some of these things are inaccessible, but you could caulk baseboards if you've got flooring that allows for that. You don't have to have a gap for expansion. You can caulk tile straight to the wall in the trim at the bottom. To stop air from moving in, you can put gaskets on light fixtures or light switches. You can put gaskets on plugs in the wall. That's a secondary measure of stopping air intrusion, but it starts at the attic level. And of course, in this picture, you can see there's cracks in the ductwork. So sealing up ductwork, we'll talk more about those a little bit later in this presentation. But around kitchen exhaust fan pipes, bath fan pipes, anything penetrating the ceiling at the top needs to be sealed. So, of course, finding those deficiencies, a lot of times these weatherization crews will have blower doors, duct blasters, theatrical fog machines or smoke machines, and infrared cameras. You guys will probably do a before and after. You do a preliminary testing. You do blower door, duct blasters. You get kind of where the house is currently sitting. You identify the deficiencies, and then you make a plan of how you're going to attack those deficiencies and how you're going to reduce the infiltration or exfiltration of airflow. And then at the end, you'll do some testing at the end. But if you have a tricky area where you just can't get to, you can use infrared cameras to identify some of these air leaks coming through and around the building or around chimneys or inside of a wet wall that's on an old building where pipe goes through that you just cannot access. And then, of course, infrared cameras can find those things as long as air is moving through it. The air temperature will reduce and you can see a pathway. And then smoke machines basically are used for finding deficiencies in ductwork. So identifying ductwork leakage, you can turn on the fog machines or smoke machines, put some smoke into that, and eventually you'll start to see where these things come out of the ducts, and you can try to pinpoint that. And of course, so we talked about a minute ago, moisture property. This is a big one for comfort and as well as durability and climate readiness is trying to overcome the moisture. So a 74-degree temperature at 40% humidity feels way different than 74 at 60 to 70% humidity. So a lot of that time comes down to when we have heat waves coming through, if you can stop moisture mitigation into the building or build up inside the building, then you can actually kind of survive those heat stresses a little bit longer, leading to the resiliency and better climate protected readiness on that. But relative humidity, it's just how much moisture is in the air, how much moisture that air can hold. Of course, the colder the air is, the less it can hold moisture. The warmer it is, the more moisture it can hold. At certain points, there is now what's called the dew point. And the dew point is going to be, of course, if you've got a cold can of Coke and it's sitting on the counter and you've got warm air around it, you see water droplets building. That's kind of the dew points or the condensation that's happening on the outside of that can. That's because the inside's cold, the outside's warm. So that happens also in a house. If you've got warm air hitting inside internal conditioned air that's really cold, there could be a dew point inside the wall that you may not see until it basically brings itself to the attention of deterioration of the sheetrock or wood, or you've got mold on the baseboards or something like that. It's going to be a dew point that's happening inside the wall. So mitigating that and not having basically it's unconditioned air or outside air uncontrollably moving through the shell is what we're trying to stop, because any warm air that makes its way in is carrying moisture, it's carrying humidity with it, and now the system either needs to run to pull that out or extrapolate that humidity out of the air, or we need to try to keep it out to begin with. So of course evaporation that occurs when liquid becomes a gas, but just the air holding moisture, it's in a gaseous state. And so once it hits a cold surface, it will return back to liquid. That's what we're trying to stop. And at some point, we can see if you start doing improvements to a home, sometimes you can see if you don't update windows, now you've got older windows that are single pane that has condensation buildup on it because you're maintaining a much colder temperature on the inside, but you've got warm air surrounding it outside and humidity that's making its way in and it's coalescing on the window itself. So we need to look at that. And some of that comes down to just fixing some of the issues with HVAC, like the ducts. And we'll talk about that later about air sealing ductwork. This is a good illustration I use a lot of times in my training. It really just kind of goes to show how we don't think of a collective. So this is diffusion. So sheetrock is not a vapor barrier. Sheetrock is vapor permeable, so air can or vapor moisture in the form of vapor can make its way through sheetrock. But looking at this, if you have a piece of sheetrock or drywall, it's 4x8 sheet of drywall. In a month's time, you can push through that in vapor form about a third quart of water over a period of a month. If you have, and this just shows an easy hole that's a 1 inch by 1 inch square, but if we have collective holes, pinholes throughout the building, the same can occur. But in that same month and period of time, instead of just a third of quart of water, you're actually looking at 30 quarts of water over a month's time. Of course, that's all going to depend on how humid the outside temperature is or how humid the outside air is. But this just goes to show the more holes that we have in the envelope, the more chances of having water vapor and bulk water moving its way in through the building. And now we need to somehow get rid of that by either HVAC conditioning, or we need to try to keep it out altogether. Of course, getting to an air barrier or a drainage plane behind cladding or bricking on the outside is just about impossible to do. But if you can plug the holes in the sheetrock, like pulling off receptacle covers and caulking around the electrical boxes, caulking around light switch boxes, fixing those things, that's the collective hole that we're talking about that can build up to a, a size that's even bigger than a 1 inch square. It can be, once you've gone around the house and you measure up all those holes around those areas, then you're looking at, almost a half a foot square of just holes in the building. So when you run a blower door test, you can do an equivalency length and it will give you an estimate of all the holes is estimated to be, uh, just for an example, 85 square inches. That's a huge hole, but you can look at it from that perspective as all these collective holes are making up bigger holes in the envelope that can now move a much more dramatic water through the sheetrock or around the sheetrock in the holes. So that's infiltration. But when we're talking about the impacts of moisture, what all can it do to the home? Of course, we all know having high humidity means it just feels uncomfortable. It's stuffy. It feels like a warm blanket we can't get rid of. But it also adds to poor indoor air quality. And a lot of times before I went through building science training, I always assumed high humidity was a huge problem and it's something that we need to fix, which it is if it goes too high. But this illustrates here that you have an optimal zone of 40 to 60%. Anything beyond that and higher, you've got mold and fungi and dust mites, and you've got possible increase in asthma and allergy attacks. But if you really look at even getting too dry, now we have a buildup of bacteria and viruses, respiratory infections, ozone production from electrical appliances inside the home. So we need to try to maintain that relative optimal zone that's there. It also adds to durability for material and buildings, making longevity of that. If you have a house that's too dry, then the wood starts to shrink and everything starts to pop and you get cracks in the sheetrock. If it goes for too long with high humidity, then it starts to swell, it starts to warp. That all is equated to human comfort. It's how do you feel inside the home? And of course, if we're now having to overcome a lot of the higher humidities due to holes in the building, we're basically just increasing energy use by running the air conditioner longer to pull out humidity. As I said earlier, 74 degrees at 80% humidity feels way different than 74 at 40% humidity. So you're going to turn that thermostat down to 72 or 70 degrees just to offset humidity to feel more comfortable. And we need to stop that from happening so that 74 is comfortable and you consume less energy and feel more comfortable inside the building. When insulation companies insulate buildings, this was, of course, pictures from the past. We now, by code standards, we have to seal up. You should not see vertical insulation in an attic. We'll talk about those a little bit later. But even on the attic floor, if you're looking at the attic floor, what we call the ceiling insulation, if you start seeing discoloration of insulation, that's basically because it's being used as a filter. So the air is moving in and out of the building shell. It's collectively setting dust particles inside the fiberglass, and it starts to discolor that. If you've already got a brown or a dark gray insulation or rock wool or stone wool, you probably will not see this. But if you have white or pink or yellow or any variants in between, you can really pick up on air leakage areas of infiltration and exfiltration on the attic floor, as well as on knee walls and under second floor subfloors, open chases around fireplaces, dryer vents, kitchen exhaust, bath exhaust. You'll start seeing all this being discolored. So it also just did the wire penetrations through top plates. So in the past, we did not have to seal those by code standards. Now in new codes, we have to seal those. That's also what the weatherization crews will do, is pull this insulation back and air seal those holes. But this is a good way, an easy way to chase these down, is when you start seeing a discoloration of insulation. And this is kind of an example. This is an exaggeration of probably not really what the weatherization guys are going to be doing, but if you could, and you removed all the attic insulation out, you can now air seal all these spots. So junctions between top plate and the wall, the sheetrock at the top, wire holes we just talked about, electrical boxes, can lights, HVAC boots, bath fan housings, around kitchen vent pipes. We talked about all those already, but any penetration through a top ceiling in the home needs to be sealed. And what you see here is actually polyfoam. It's orange because it has a flame retardant that's in it. It actually does meet most of them. If you find, if you read the can, they do meet the fire code for this to be a draft stop for fire protection inside of a building. But in our world, in the energy code world, we use this for air sealing. So it can do two things at once. So air sealing vented can lights, a lot of times we don't really use these in new construction, but in the past we used can lights that had vents on the side of it that keep those things from overheating and possibly causing a fire. So the heat of an incandescent bulb was so bad inside of a metal can that it had to be vented to the attic. A lot of times your crews may not be able to have the funding to be able to change all those out, but there are ways to mitigate that. You can, of course, just seal up the can, but it's very strongly advised that you do not use incandescent bulbs anymore. You change these out to CFLs or LEDs that have a lot less heat that's given off of that. The newer can lights that are out there are IC rated, so it's insulation contact as well as airtight. But this little the illustration I got off the internet basically just shows it's a styrofoam or kind of like an egg crate dome that you can put over the top of it. You just seal it to the sheetrock with either foil. They're using a 181 foil. You can use polyseal. You can use caulking, anything like that. But it's best to retrofit those cans to not have a buildup of heat inside those cans. This is showing an LED retrofit kit that just screws into the base of the bulb. And then you've got that. You can also get LEDs that are just a bulb looking, and you just put it back in there. But if incandescent bulbs are left, please avoid all contact with insulation, because if they're not IC rated, then you need to avoid that. And then, of course, seal up the wire penetrations throughout the box. is the best way to do that. So there's several different ways to do it. This is another one I found as well. A lot of the weatherization guys carry these in their trucks. This again is you do it from the inside instead of the attic level. Is you unscrew the bulb and you pop this in there, and it's got a gasket at the top and the big ring at the bezel, and it snaps into that can and air seal those cans. Again, it's highly advised to not use incandescent bulbs. So if there is an incandescent bulb in there, those need to be removed, and we use cooler CFLs or LEDs. But this will make the existing cans airtight. It's a great way to retrofit these cans when they're not accessible, like in a cathedral ceiling. I've got some of those in my house that I cannot access. So this is about the only way I can get those air sealed, is to put these kind of retrofit pieces in there. And then of course, air sealing HVAC boots. This is something that your crews will do out there, is sealing the gaps between the metal boot and the sheetrock or the ceiling. You can do it from the attic side, you can do it from the interior, but it's always advisable, in my opinion, to do both. That way you make sure you get it sealed. Sometimes those boots are so tight to the wood that's in the attic that you can't get to one side of it. So the only way to do that is to remove the grill inside and then caulk around the sheetrock. So that's a great way to air seal those as best that you can. That also can stop a lot of moisture mitigation around those, and that's usually where the cold is hitting hot air from the attic. In these grills, sometimes when you go into an existing home, you'll see evidence of rust on those grills, and that's because hot air is meeting cold air and it's starting to condensate, just like a cold can, on those vents, and that's something you'll need to remove and replace. That way, it can be you can mitigate the moisture coming into the home, and you also make sure that that air temperature that's coming out of that vent is making it into the home to keep it more comfortable. So this was a little bit harder to do than it sounds and what it looks like here, but blocking and sealing subfloor openings, most of the time that means insulation will need to be removed. And then you should not be able to stick your hand up underneath those floors. That's kind of how these floors were built in previous construction. Is it basically it's just one floor over the other, and that's a misalignment of the thermal boundary, is because we now can stick our hand up underneath there. The floor underneath that subfloor doesn't have to be insulated because it's over conditioned space most of the time. But this is stopping that, and it's building that barrier so where insulation can stop, and now you're not getting air intrusion in that. So as you see here, they did remove the insulation. They've cut some foam board. They've polysealed around all the openings for that. And then you'll actually put insulation back over that. Now you've aligned the air barrier as well as thermal insulation. So you've created a thermal boundary here at the band joist. But that's sealing up all those. We just want to ensure that the insulation's in contact with that as well when you're done. Of course, it says prevents pest and moisture intrusion under the floor. What we're looking for is trying to keep the home more comfortable and keeping that second floor from overheating because there's no insulation underneath it. And then, of course, stop air around windows. Of course, caulking around windows and doors is already in your scope of work. We see here one person's caulking the inside and then one person's caulking the outside. Windows and doors are just holes in the envelope to the outside that are openable or see-through for fixed windows. So we need to plug the holes that are around that. So a lot of times in new construction, you have what's called the rough opening, and then you're going to have to caulk or seal that rough opening to the framing so that those windows and doors are airtight. It's harder to do when you've already got sheetrock on there. You can't reach the rough opening. So that's why we have a finished trim of caulking around outside of the windows and caulking around the inside of the trim inside the home. So that's the best way to mitigate that as well. And then, of course, sealing up doors. As I said a minute ago, windows and doors are just openings to the outside. They're holes in the envelope. We need to do everything we can to seal that. This illustration is just showing a foam gasket. Don't really recommend that because they deteriorate quickly over time, or quickly. Just due to wear, opening and closing of the door, and then if it's exposed to UV, it deteriorates extremely fast. These little nail-on or screw-on with the gasket is the best way to do it, is just nail it or screw it to the outside of the trim, and so when the door is shut, it actually goes up against that little bubble or rubber gasket that's in that, and you air sealed that door all the way around. Sometimes it will take tightening those screws a little bit, not over tightening them, and then shutting the door and then adjusting them and then retightening the screws. That's usually oval shaped in those grooves. That way you can move and adjust that weather stripping to meet that door. And then just explain to the homeowner over time those things may also shrink, and then it'll need to be readjusted from time to time. So that's the best way to air seal that. And then, of course, weatherization or weatherizing the pull down stairs, attic hatches. We'll see that one on the next slide. But this is a pull down stair that's in the conditioned space. So it's over a conditioned space from an unconditioned attic. So if you have that, if you have a pull down stairs in your garage, doesn't really matter. But if it's in the conditioned space, again, on the left-hand side, you see that he's caulking around the rough opening, the framing around the pull-down stairs. So it's always best to do that. And the one in the middle, he's doing a peel and stick. Don't recommend that, but if that's the only thing you can do because it's an older stairs, then that's the only way that you can do it. And to make sure the homeowner realizes as those things get deteriorated and or pulled off over time is to go back and get those things resealed from time to time. And on the right, I just want to put this on there. It's not really air sealing, but it's kind of not really insulation, but it's what we call radiant barrier or bubble wrap that's basically using it as an insulated cover. This actually gets stapled around the stairs, and then you have a zipper that you can zip and open up and go into the attic. Even though they don't quote unquote have an R value, you can see the difference with an IR camera that it does stop heat intrusion into those doors. If you look at that door in the middle, it is not insulated. So if the attic is 160 degrees, that door will be 160 degrees, and it's just radiating heat into the house. If you put what you see on the right there, if you put that attic tent on top of that, it greatly reduces heat inside the home itself. Keeps that from overheating. And as I said a second ago, the scuttle holes is also a point of contention, is to make sure that the top of those things are at least insulated to an R21. As you see there, the EPA's put their little smiley face with a thumbs up that says that looks good to me. Adhering it with glue or tape or staples or other material to hold that in place and make sure it doesn't slide off. Or sometimes you can just slide it on and then just push it down. But then add weather stripping. If it's an accessible scuttle hole, sometimes these are not meant for storage, so that you can just caulk those shut. And you should still insulate those, but you can caulk those shut. And once you caulk those shut, you won't have any air intrusion. But if it is accessible and the homeowner's using it for storage, again, we show a peel and stick gasket that's there. If it's used a lot, it will deteriorate over time, and just let the homeowner know that they need to have that fixed or addressed from time to time. And then, of course, insulation. That you guys are more than likely going to be putting more insulation in the home itself. So almost any material can be used as insulation as long as it can trap air and slow down heat transfer into the building. So we've seen denim, we've seen recycled newspaper, which is called cellulose. You've got styrofoam, you've got spray foam, you've got, well, it shows on here mud, water, anything can be used as that, but you're not going to put that in your attic. But a lot of times recycled materials and fabric can be used as insulation. Most of what we see is fiberglass. So just blowing more fiberglass into the attic, getting more acceptable R value that resists the heat transfer into the building. It's basically used to determine the material, which material is good insulation. You're looking at, if you see the picture there, we've got markers that will show us what the R value or equivalent R value of the depth being used, what the R value is in the attic. So that's what we need to look for at the end. But most of the time when the crews get there, they're going to take a reading of what do you currently have, and then how much are we going to need to add to the top of that to get the proper R value. All we're trying to do is resist heat transfer into the attic. That's why we need a lot of that fluffy stuff in there, because in Texas, if we have attics that are 130 to 160 degrees, that heat is trying to get to colder air, and the colder air is inside the home. So once heat hits that insulation, it goes through the minute air pockets, and through conduction, it's going to start making its way into the sheetrock. Hopefully, by the time it reaches the sheetrock, it's closer to the air temperature of the inside of the house and not the attic itself. So that's what we're doing, is resisting heat transfer into the building. And this is new to the code. I'm not sure if the weatherization crews will be doing this, but this is a good way to uphold the insulation to the outermost area of the top plate. So this is a person standing in a attic that's over a garage, and then what you see where the pink fluffy stuff is, that's attic over a conditioned space. So in the 2021 code and beyond, these are now required. I think it's part of your weatherization scope of work is putting attic insulation dams up. So this is between an unconditioned attic and an overconditioned attic, and it's between porches. It's between ceiling height changes. Any place that we need to have a full depth of insulation is going to require some form of dam to hold insulation to the proper depths that are needed. This is now code required. So before we would always taper it at the end so that the insulation didn't fall over the top plate where it's not supposed to be, and that was leaving not enough R value over the top plates, which is heat intrusion into the building. So now we put these dams up to uphold the R value required all the way to the edge of the top plates. And then one thing I want to talk about, and I always try to go through this with some of the stuff, is we have homes that we are trying to get airtight, and making a home airtight basically holds conditioned air longer inside the building, leaving it more comfortable. It's more climate ready. It's more severe weather event readiness. It's just us trying to protect ourselves from exfiltration and infiltration of buildings. However, once you start doing that, then there is a buildup of particles inside the building. We call it PPP, so it's parts particulates. That's parts per million or ppms. So how much in parts per million are we trying to mitigate or dilute or exhaust? And of course, what could those contaminations be made of? And a lot of it is if you've got brand new carpet and flooring and cabinets and the glues in that, the carpet fibers, the paint, even low VOC paints have VOCs in it. Stains, new insulation, pet dander, products from cooking, most cleaning products. If you can smell the the perfume or the cleanliness of a product, then that's a chemical that is actually built up of parts per million. And some people are more susceptible than others. The elderly and the young adults could be more susceptible to levels of parts per million that most people aren't. If you have a young couple in the home and they are in and out of the building all the time, it will exhaust itself or dilute itself. But if you have elderly or younger kids that are mostly in these homes that you're air sealing and making them tighter, we now need to be concerned with, well, we need to mitigate that parts per million. So I believe in your weatherization scope of work, you're going to be putting some kind of mechanical, we call it mechanical ventilation or fresh air into the building. So that's what we want to do. Sometimes they look like this. This is a standalone inline fan that actually is going to draw air out from the outside inward, and when it does that, it's going to dilute the contamination that's there. It'll reduce the parts per million. So we always say, do houses need to breathe? Well, yes, but we need to want to control how often and when. In new construction, these are required. Because the home and the building is being built tighter, we have to exhaust or dilute the contaminations inside the building, what we call adding fresh air to it, or we exhaust it out with bath fans, kitchen exhaust, or the like, and we're reducing parts per million. But now in a home, when we have it here in Texas, this side of Texas being warm and humid, we don't want to draw the house into a negative because it's going to pull humidity inside the wall. And we said earlier we want to control that humidity from coming in. So we're going to actually pull air and supply air inside the building and actually slightly pressurize the building. So any humidity that gets inside there is trying to force its way or push its way to the outside. There are more expensive products that you can use to do this, but these are some of the ways that are being used in new construction. Benefits of mechanical ventilation: better indoor air quality, more control over, in other words, if the house just doesn't breathe on its own because it's now uncontrolled, that basically improves the comfort of the building. We're maintaining a more constant flow of outside air to the inside. We're providing filtration as well as pushing it through a dehumidification using air conditioning on the incoming air. So you're pulling humidity out of that. So this illustration is basically showing if I do exhaust only, then it's going to depressurize the building. If I do supply only, it's going to pressurize the building. If I do what's called a balance, then it's going to be balanced pressure inside the building. And we won't go down that rabbit hole, but if you have supply only or exhaust only, well, now you're creating pressure imbalances inside the building, which can lead to comfort issues. But that's a whole different topic we can go all the way down through. But as we just said a minute ago, negative pressure is not what we want in Texas. Balanced is kind of too expensive for adding things. That's an ERV and an HRV. We don't really want to go to that expense. So we usually do a slightly pressurized or slightly positive pressure inside the building. So pulling air from the outside in, slightly pressurizing it, and you're pushing some conditioned air into the walls, but you're mitigating uncontrolled humidity and temperature to come through the walls. That's what we want to do. That's ideal. So systems that can be integrated, we showed the one on the bottom and the middle, but to the top left is the least expensive way. It basically uses your HVAC unit to run a fan that brings outside air in, and it's based on size of the home and number of people inside the building. It will come on a certain time every hour and actually run the system to pull outside air in. What we're doing is diluting contaminants in the home. We call the ones that are on the bottom and to the right a standalone fan system. These most of the time have humidistats and temperature sensors in them, so you can control when it's being used for outside air that's humid or too hot, especially around in Houston and south of Texas. You don't really want to pull in 108-degree temperature. So it will sample the air and then shut off. It will run when the air gets cooler at night. It remembers when it didn't, so it will run long enough to dilute contamination. The one on the top left, it does not do that. It will pull outside air through the system, and the system will distribute it throughout the home, but it will not. It does not know if the air is too humid. So hopefully, a lot of times when these things run during the summer, it will run with air conditioner, so it will dehumidify. But during the winter, it's just going to pull in outside air as it is. So depressurization concerns, a big thing that you guys you're trained on for weatherization is creating a worst case depressurization and testing that to see where you're at in the building. But things that can depressurize the building. So once you start plugging all the holes on the ceiling and around the light switches and the plugs and the baseboards and the top plate and the can lights and the HVAC boots, once you've plugged all those holes, if there's a gas-fired appliance inside the building, then depressurization is a concern. So if everybody turns bath fans on and kitchen exhaust, the dryer's running, the fireplace is running, you've got HVAC imbalances, you've got wind on the outside causing pressure imbalances around the building, it can depressurize the house. And if it does, we need to mitigate that, because if you have a gas appliance inside the home, it could possibly cause safety and health concerns. So we need to mitigate that. And we do that in several different ways. You either isolate the closet or the system that's a fuel burning appliance, you isolate that from the conditioned space. In other words, if a kitchen exhaust being turned on with the dryer running is going to depressurize the house, well, I don't want that to happen around a gas appliance. So if that's the case, then I'm going to weather strip the door. I'm going to put weather stripping on there. In the water heater picture you see on the bottom left, you see a silver pipe in the back. That's giving it makeup air or combustible air. And then the top left of that picture, you see an upper vent that will vent any other contaminations that are floating to the top, will exit through the building. So that's what we want to do to mitigate depressurization concerns inside of an existing home. This is one of those that even in new construction, it could possibly happen, and it did happen to me in doing inspections for new construction. Suddenly a builder was building rentable property without garages, so the only other place they could do is put these systems inside the home, and they did not mitigate that. They did not have high and low pipes. They left the door as unweather stripped and did not have a threshold. That's going to cause a concern, especially in a new home. It's going to cause a concern when exhaust fans are turned on. So we'll make sure those are done in any way possible to seal up that cabinet. Duct leakage can cause depressurization, so you want to make sure that duct leakage is handled as well. If the door is louvered, sometimes you'll need to look at either replacing the door or trying to seal that from the inside. But health and safety just goes without saying, is if you're going to seal anything up, you need to make sure that it has a way to get air. Just like that water heater picture in the middle is high vent, low vent, required by the mechanical code. You got to have that. You got to give it makeup air. if you're going to seal it off from the home, which is advisable if you're going to air seal a home and make it more energy efficient. So, of course, with that, I just put on here energy audits. This is kind of what your weatherization crews will be doing. Is you're identifying areas of energy loss in the home around air leaks, insulation gaps, inefficiency windows. You're evaluating the heating and cooling and ventilation system. You're looking at, are there pipes that are rusted? Are the slope of the pipes the correct way? Is the duct sealed without a lot of holes? Is it insulated properly for the duct system? Just evaluating that system, and then of course provide a roadmap for cost-effective improvements. A lot of times they're going to have to look at this by priority of what's the biggest priority that we need to tackle. And for me and my standpoint, when we're looking at it from code construction or code stuff, is you're looking at, well, what's the best way I can make sure the homeowner is comfortable, B, we're going to actually do health and safety concerns, and C, make sure that we're looking at climate readiness, resiliency to extreme weather temperatures or weather events that are outside, and durability of the building. And of course, again, with all of this, you're going to lower utility bills by reducing wasted energy. You're going to improve the indoor air comfort. So now suddenly someone will feel different at the same temperature they normally set it at. They're going to find themselves raising or lowering the temperature depending on the time of year, and they're going to reduce their energy consumption because they feel more comfortable. It enhances indoor air quality by addressing ventilation and moisture issues. We talked about how that happens already. And then, of course, increases home's durability by preventing all that moisture and humidity coming through there. And it can add value to the home by documenting the energy efficiency upgrades. Anything that you get from a energy audit company and or weatherization crew, make sure you keep that, because when you go to sell it and you give it to the real estate agent and say, hey, this might help, a lot of times they can document that and show that improvements have been made and that utility bills were lowered due to the fact that weatherization was done to your home. And then, of course, it can support eligibility for rebates, incentives, energy efficiency programs. If a unit has to be replaced, make sure you check the manufacturer and or the supplier's website to see if you've got a rebate available. Sometimes there are tax incentives as well on that you can take advantage of. And then an energy professional, this is kind of what weatherization guys are now. It used to be they just did it by site. Now they do it by testing equipment. This is really equivalent to being an energy professional in new construction, is being a weatherization company or weatherization crew that has blower door, duct blaster, and other type of testing equipment. But from an energy professional standpoint, we must understand, as we talked about in the very beginning, is the basic energy principles. How does a building work as a whole system together, and how is that affecting the energy consumption? And then we'll recognize the energy saving opportunities. Hey, we're going to seal this ductwork. We're going to seal up the attic insulation. We're estimating that we can drop the blower door testing down 1,000 CFM. Translate that into energy savings into dollars so the homeowner can see this is how much we're projecting that you're going to save. And then we'll evaluate and measure the building performance before and after to make sure that we're actually meeting those targets. And they're going to also know the incentive rebates and tax benefits. We just talked about that. And they'll also explain conservation procedures and goals. So a lot of times it's explaining to a homeowner that, hey, we've air sealed your home. We dropped the blower door test down 1,000 CFM, which is a lot. But if you're able to get to that point, you may explain to them that, if you like to keep the thermostat at 74, try 75. Or if you like to keep it at 72, try it at 74. Just to see if that's more comfortable for you, because now it's going to be a drier air. It's going to feel colder than it did before. And then educate them on how to use it more efficiently. So if you guys install a programmable thermostat, please explain to them how you program it for a daily and a weekly. So that way, if they're not home and they do spend their time away from the house by going to work, that the thermostat will adjust by a few degrees when they're not there, and it can readjust to have it ready for them when they come home. So explain to them and educating them how to save it and how to conserve energy and save money. The blower door test, we talked about it a little bit earlier, but really all you're doing with this is you're estimating leaks throughout the building's envelope. So basically you're depressurizing the house by drawing a fan into the building, and you're sucking air through all the holes in the building. There's a standard measure of pressure, which is 50 pascals. That's the standard pressure that you have to use. There's a manometer, which looks like a big old calculator. It can calculate and use, it shows you CFM, and then you've got to calculate what air changes per hour, ACH, is, to be able to try to find out, well, what's my ACH target I'm looking for? Or you're going to go a percentage of CFM. So all you're really worried about is how much in CFM can I drop this? So ways to mitigate that we've already talked about was complete the air barrier, plug all the holes, sealing all the penetrations in the envelope, adding weather stripping around doors, attic doors, scuttle holes, hatches, the garage door, any place that's to the outside, caulking around windows, caulking around doors, and you'll be able to tackle that. But that usually is the list of items that you'll list in your scope of work about how you're going to better air seal a home. And all you're doing is going to be putting this blower door up, depressurizing it. And we talked about it earlier. If you're going to depressurize, the longer you run the fan, the more exaggerated this temperature difference is going to be. As air moves across anything, the temperature itself will lower. So even if you have 74-degree air in the home and you turn that fan up and you run it, if that air is moving at all at a fast speed, it's lowering its temperature. You can now see and identify this on an infrared camera, and you could start to pinpoint where this is happening. This picture here doesn't really illustrate that. This is just showing heat that's leaving the building, not really typically in an airflow manner. It's a combination of airflow, radiant, conductive, and convective heating that's actually leaving the building. So this appears to be in a colder climate, and the roof itself, the decking on the roof is red hot. So we know that we've got a lot of air leaks in the building because it's all going to the attic and finding its way outside. These are the things that we're going to have to mitigate. But if you have an infrared camera and use it in conjunction with your blower door, the longer it's on, the more the air temperature in that leaky air is going to be showing up on your camera, and you can pinpoint that a little bit easier. And of course, also with doing pressurization testing on the envelope, we're also going to do pressurization testing on duct systems. So we call it duct blaster. Some people call it duct blast, and sometimes it's just duct test. But we, again, estimate possible leaks in the HVAC system. These things do not pinpoint leakage. It doesn't say, oh, I now know where to fix this. It just says, this is your estimated leakage. Now it's up to you to go find it. And as I said earlier, they can use theatrical fog machines. You push fog or smoke through this, and it actually will show up on the leaks. You actually do the same thing as you do a blower door. It's a standard pressure of 25 pascals, which is half of the envelope. You still have a manometer. It still gives you CFM, and you can equate that to how many CFM per 100 square feet. Code is 4% or 4 CFM per 100 square feet. You're going to look at a target of what you can drop. Not everything can go to you can't get to the ideal, oh, this is just as tight as new construction. A lot of times these ducts are not accessible, or there's just so much that it will take you forever to fix it. But dropping it down a certain percentage or a certain CFM or percentage of CFM is going to be your target. And of course, ways to mitigate that leakage is to seal the connections with mastic. Using proper techniques for mastic, following the ACA standard for mastic is basically the mastic needs to be the thickness of a nickel and go 2 inches on any connector before you put the flex duct on it. If it's metal, then that's different. But on flex, when you're trying to seal it up, which is predominantly what we see in homes, is you're going to do the thickness of a nickel, 2 inches down on the collar, and then you'll put the inner liner on it, put a zip tie on it, use the proper tensioner to tighten that up, and then put mastic over it, and then put insulation back on it. That's going to air seal it. Then when you caulk the return registers and the supply register to the sheetrock, that's another area of leakage. You can also have areas of leakage around doors, filter doors on the unit. The unit itself can also leak, but some of that is not fixable. You can use tape. As long as you use a 181 UL approved tape, you can do that and then seal that up, or you can just use mastic and paint it on those systems as well. And of course, this is kind of in lieu of new construction is manual J and S, which is load calculations for the home. I believe the RedCalc software kind of runs through some of this stuff, but basically, as codes start to get more stringent, anything beyond the 2018, it now says in Chapter 5 of the code book, it says existing homes, if you do a full system change out, you need to do a proper sizing calculation. That's manual J and manual S. The J will give you how much heat is entering the building in BTUs. The S will match that equipment in BTU output to the heat load coming into the building. For 2024, and soon is coming to Texas with the adoption, any what they call, and I'll do air quotes, any substantial changes to the system requires the equipment follow the requirement using properly sized calculations. So if you're replacing all of the ductwork, that's going to be a substantial change. Should have proper sizing, but I know you're not going to change the equipment out if you're just doing ductwork changes. In the 24, you also now have a requirement of manual D, which is duct design, proper sizing, and proper duct run. How many splits, how many Ys, how many Ts. That's new to all of that. Probably not in the scope of work for WAP. But just to keep in mind with that is new construction or complete replacements should be looked at as, well, let's do a manual J load calculation. Make sure this house has the correct size of equipment in it to begin with before we just replace it. 9.5 times out of 10, it may be oversized by a half ton to a ton, which means A, you can save money on replacement of the equipment, and B, the home will actually be more comfortable. The system will run longer, pulling out humidity, and now you're going to be able to address that humidity control inside the building. Homes like mine was built in 1994. It probably from day one had over a ton of air leakage through duct systems that were not properly sealed. So by the time I changed it and got them all air sealed with less than 60 CFM of leakage on a 4-ton system, well, now the home stays a lot more comfortable. The temperature has dropped to the point where now it comes out 50 degrees air, 55-degree air, instead of coming out like 72 or 68 or 64-degree air because all of the air leakage. But the system was oversized by a half a ton, and then the duct system was well undersized. That's how they used to do it religiously in new construction. So doing proper size calculations are needed on full system changeouts. A good way to also mitigate some of that heat loss or heat gain in the system is also making sure that refrigerant lines are actually insulated properly. Code requires them to be a minimum of R3 because they carry a temperature that is lower than 55 degrees. So if a temperature is lower than 55 degrees on that, usually the bigger pipe of that, the larger vapor line, the suction line, vapor, it's used in conjunction with each other. But these are required to be insulated to an R3. They must, on the outside, have a UV protection on it that's either painted or use something called Armaflex. It provides a moisture protection. If it's going through the wall and it's sweating, then you've probably got condensation happening inside the wall, so making sure it's properly insulated. The pictures I've got here is one's the outside, which you see the insulation has deteriorated over time. It did not have a UV protector in it. And the one on the right, actually, you see they shortened it or did not seal it all the way or insulate it all the way to the cabinet. So more than likely that last little 3 or 4 inches of that pipe is going to be sweating. There's a drip pan underneath it, so it's not going to get into the home itself, but it's gaining heat from the attic. So it's best just to make sure you're insulated all the way to the cabinet. So it's estimated that for every 1 degree increase added results in 1 degree less of cooling temperature. So if you see these pipes being uninsulated and it's able to gain a degree, then instead of 58 degree air, it's 59 degree air. So it just leads to that I don't really feel comfortable anymore, and it's not the most efficient, so we need to get those air sealed. And of course, tape the seams and seal all the seams that are in that. HVAC coil cleaning is also another way that weatherization crews can come in here and make sure the efficiency of the equipment is a lot better. It's basically just cleaning dirty condensers that are outside. It restricts heat rejection, which is what you're trying to do, is blow heat off of it. This causes higher head pressure, which leads to inefficiency of the equipment. The dirty coil can basically reduce system efficiencies by 5 to 20%. For example of that, you've got a 14 SEER performing at only 11 or 12. So in your red calcs, you're going to put on there what the SEER rating is by the manufacturer's nameplate. That may not be what it's performing as, but that's what it was when it was new. And then, of course, clean coils can also reduce amp draw. That's saving you on energy consumption, is reducing the amp draw by 5 to 10%. And then clean coils also can extend the life of the equipment and have fewer breakdowns. So it's always good to explain to the homeowner this should probably be done at least a minimum of every 2 years, probably every 1 year or every year. It's just removing the top of it and hosing it down. Or if it's an elderly couple that's there, they really kind of don't even need to pull that top off of it. It's just spray it down with the water hose and try to clean off what they can from trying to get those condenser fan coils cleaned off. That's the best way to do it. And we talked a little bit about this a second ago, but sealing duct leakage, this is kind of what it looks like. You see on the left, properly sealed. They've got the insulation sealed to the system, which is sometimes a good thing, sometimes not a good thing. The outside jacket that has the insulation in it is not what you're trying to keep air inside of. It's the inner lining. So we want to make sure, looking at that inner lining, to make sure it's sealed first before we just put insulation on it. This is basically keeping insulation all the way to the cabinet. It's reducing condensation around the collar. But if we can't inspect this to make sure that it's air sealed properly, or you're doing a duct test and you're finding you're failing and all this is sealed, you're going to have to cut all these off. And then, of course, on the right, if you've got metal piping, this is basically he's using a fiberglass mesh tape to actually get the mastic to adhere to both dissimilar materials. That's a good way to do it. But just to make sure that you paint enough on there that you're not seeing that stuff come through, you're not seeing the metal show through the brush strokes, you're actually seeing that it's properly sealed by mastic. That's a really good way to do it. And then one thing that a lot of times, if you do a duct test, it's not too bad. You're able to air seal some of that, but you want to make sure the homeowners has the best comfort protection that you can. It's just mitigating airflow issues. This is something that Energy Star brought out, and now code actually follows this as well, is looking at proper duct installation and trying to grade how well is it done. Anytime you see what's on the left hand side here, we have ducts leaning on framing members, not a good thing. That piece of wood is going to get to 160 degrees. All that heat will transfer directly into that duct. The airflow going into the building is now going to be carrying warmer temperatures and more humidity inside the house. So strapping that to the ceiling and pulling that as best as you can, to even giving a 1/4 inch to a 1/2 inch gap will mitigate heat transfer into that. The outer jacket of these things are the same thing as radiant barrier. They hold heat. They don't absorb heat, or they absorb heat and don't re-radiate it. But once you have something come in contact with it, it transfers heat immediately. So it's best not to be in contact with any type of building materials if you possibly can. The one on the right hand side, you're looking at sagging ductwork. It doesn't look like it's a big deal. I mean, if you've got air moving through it, I mean, is that really causing a problem? And the answer to that is yes. It's what's called friction loss, where you see that lowest point of the ductwork. You've got air that's trying to travel in a straight line. If it now is ricocheting off the side of that duct, it's causing turbulence. It's called friction loss. The air is spinning instead of going straight forward. It's now ricocheting and spinning and not making it to its destination. So lifting that centerpiece and having it as straight as possible is really the outcome that you need. This is a sag that is too much, even for code standards on new homes. It's too much sagging and needs to be fixed and addressed. Same thing with things like this. On the left-hand side, of course, we have no mastic on the collar at all. So with that, you're going to get a ton of air leaks. On the center picture, you're actually seeing a ductwork that's compromised by bent over. It needs to be a sweeping turn if you can, so they'd have to basically cut that top strap off. Looks like they tried to adjust it a few times, but if you have to, just kind of, I don't know how you would fix this without cutting the duct and making it shorter, but a sweeping 90, not a sharp turn like this. Anything that's less than 90-degree bent is going to cause airflow problems. Same thing as what we talked about earlier. Air is going to hit in a straight line. It's going to go straight to the top of that peak. It's going to ricochet backwards. It's going to get stuck inside the ductwork. So doing a duct test isn't going to find it. When you do a duct test, a lot of times if you have to overcome these things, that's why you're turning your system up too high, is because you have friction loss inside the ductwork and you're equating that to duct leakage when it really isn't. And the picture on the right-hand side, of course, again, pulling insulation back and realizing I can see directly into the house because the insulation's pulled away from it. So making sure that's fully insulated all the way down to the boot itself is a way to mitigate having heat transfer. This is, again, just field pictures. These are things I took when I was on new construction inspection. So yes, Does it happen in existing houses? Well, it did happen when the house was new and it probably was never fixed. What you see on the left is there is mastic on there, but they did not mastic the collar as they should. They mastic around the plastic. So from the untrained eye, it looks like it was sealed, but it is not. That needs to be pulled off and mastic correctly. Otherwise, you will have too much leakage through there and you won't get that fixed or addressed. Same thing on the right hand side. There's just not any mastic on the collar. They did not mastic the collar to the plenum. They did not mastic the duct to the collar itself. So pulling that away with no evidence of mastic, you're just going to have duct leakage that's happening there. That needs to be mitigated. So with that, that's all we've got for today. I'm done a little bit earlier. I probably talked a little too fast, as I always do. This is our Connect with Us page. We've got our main phone number there. We're all on our website is eepartnership.org. We are always partnering and love to partner with HARC on doing weatherization and WAP training, as well as doing other webinars when we can. We're also on Blue Sky. We're also on LinkedIn at Spear, and we're on X at eepartnership.org. Feel free to reach out to us anytime you have any questions with things. This is my personal information. Feel free to snap a picture of that if you'd like. Call me, text me, email me. I love getting pictures from the field so I can use it. I usually will try to credit those people that have sent me photos, and I can put that in my presentations and credit them from that. I thank everybody for being here. I appreciate you guys being part of this WAP training that we've gone through for HARC, and I appreciate HARC for everything that they've done to support Spear. And thanks to everybody again for being here. I appreciate it.